10 and 11. Yeah. So we'll keep use the same scantron for the last 3 chapters. Tuesday we already finished chapter 9. So we start on chapter 10 today. So like today and then next week Tuesday we'll study chapter 10. And then the last day of lecture, which will be next Thursday the 10th. And we will finish the chapter 11.
You have our schedule.
I have you should turn in the you turn in the schedule. Yeah, so let me give you back the schedule. So for chapter 10 you will start on 21. Right. So chapter 10 is the second chapter of chemical bonding. And in this chapter we are going to study the more chemical bonding series, but that is not that important. More important is use the Lewis bonding theory, try to predicting the geometry of the molecular, polarity of the molecules. To do that, I really depend on you to be able to draw the Lewis structure very quickly, and also be able to identify those different electrons on the atom. It's patterned on the central atom. Right, so let's review that concept of those different electrons on the atoms. And so some of those electrons on the Lewis structure, we call them lone pairs. And there are other electrons, we call them bonding pairs. Okay, so the bonding pairs and lone pairs is very important on the atom. It's patterned on the central atom. So let's start with this question. How many lone pairs are found in the caffeine molecule? So this molecular structure is the caffeine molecule. Usually, as you study more and more chemistry, so sometimes the chemistries will omit. You get new scantron for the new chapter. You will for this chapter 9, chapter 10. You start the CRE, so this will be on your 21 on the scantron. Use the same scantron for chapter 9. Okay?
I'll use the same one?
Use the same one for chapter 9. So therefore you will start on 21.
So we don't have to technically turn it in?
You don't have to turn in like until, yeah. So we'll keep all the 3 chapters on the same scantron. Alright, so as I said, most of the time the chemists are omitting those non-bonding pairs. For example, this oxygen right now has only 2 chemical bonds, which means has 4 electrons when you count in the octet. There are different ways to counting how many electrons on the atom. Okay? When you count in the octet, when you draw the Lewis structure, so those electrons shared just totally belong to the atom they are shared. Belong to both of them. Okay. Okay. So what do you think? I start with this O with 2 more pairs, so that the sort of long pairs. And then this question asks you how many long pairs all together in this molecule. Okay, see which atom need more pair of electrons to make the octet if they need the octet. And then you add them together, see how many all together. So I start with this I put 2 more pairs. Because right now there's only 2 pairs. And O is not the exception, so oxygen need the octet, which means need 4 pairs.
Is it E?
D?
D.
8 pairs. Okay, so where are 8 pairs? So these 2 pairs here. And now where are the other pairs?
Oh, on the other oxygen.
Are the other
That's fine.
more pairs?
That's double bonded there. Everything there.
And then what else we need more pairs? Then now we have 4 pairs. Altogether, only the E, we have 8 pairs. Where are the other 4 pairs?
Oh, and nitrogen.
Nitrogen, 1 pair, 1 pair, 1 pair,
Yeah.
and 1 pair. Okay, let's talk about pairs.
Oh, pairs, okay.
So you have 8 pairs. And obviously, if I ask you how many electrons, you will see like the 8 times 2 is 16. This question, how many pairs? Okay, very straightforward question. Okay. So you will keep practice. So this problem, I give you the loose structure. Okay. If I don't give you the loose structure, again, you have to be able to draw the loose structure very quick. So this structure, what we're going to use is we're going to use last program, those kind of loose structure to determine the molecular geometry. So molecular geometry is complicated. Like in the last program, you will see what is the geometry for this molecule. You cannot see in one word because there's quite a few center atoms. And for each center atom, what we're going to study in this chapter is about what is the geometry. Okay? And so the geometry for the molecules depend on the electrons. So basically, like you will see, the molecules are 3-dimensional objects, and for each of those center molecular, like a simple one, like water has 1 center, and you just specify what is the geometry for that center atom. If you have more than 1 center, you specify for each center what is the geometry. Use those names we are going to see in this chapter. Okay? So for each center, you will describe the molecular geometry as those geometric figures. And so those geometric figures you're going to talk about in this chapter, they will have those corners, and those corners will indicating the position of those surrounding atoms, and the center atom will be somewhere in the center of the geometry. And so then you will see what are the names for those geometry. And in this chapter, you're going to see 11 of those names. And once you have those geometry, you just imagine, or you will see those connection, or the line between the center and the corner. And then you will see the angle between each line. Those are called bond angles. And to get those 11 geometries, we start with the Lewis structure. Once we have the Lewis structure, we will first get this new concept called electron regions. Okay. So now this is our second way of counting electrons. Our first way of counting electrons is counting the orbitat, the superorbitat. Okay. Now our second way of counting electrons, once you get those orbitals, once you get the loose structure, you will see like you mainly like focus, concentrate on the center atom. So on the center atom, how many regions of electrons? So this name, region, is same as groupers, same as domains. Now let's talk about what we mean by these 3 names. These 3 names are equivalent, all means the same things, depending on the book. And so once we decide how many regions, and then we will use one simple theory to predict. That's a good theory, very simple, but that works for most of the programs. But some of the programs were not really, the result not really what you predicted, because your prediction cannot predict 100%. So that theory used to predict those geometry for those regions is called the whisper theory, called the valence shell electron pair retardation theory. It works for most of the program, and you have to be able to like draw the Lewis structure. We still use the same scanner for Chapter-10.
Oh,
So you have it here. Right, so that electron, that so-called whisper series is pictured by this simple picture. That means when you have those electron groupers, maybe a lone pair, maybe a double bond, maybe a triple bond, whatever that region you have, they're going to repair because electron has negative charge, and naturally everything wants to be stable, which means want to have a lower energy. So how can you get lower energy? Is spread out as much as possible those repulsions. So now let's see how to count that electron region, electron groupers. So I will mainly talk about two ways of counting those regions. One way is the book way. So the book will tell you for each lone pair, or lone electron, not bond electron. Or here we'll see later on we'll see the single electrons. So for each lone pair, we count them as one group. For each single bond, you count them as one group. For each double bond, you count it as one group. So that's a little different than when you count in the orbital. When you count in the orbital, if you have a double bond, you see there are 4 electrons. But when you count in those grouper or the region, so that 4 electrons in that double bond all together counting as one group. Even if you have a triple bond, if you have a triple bond, then you have 6 electrons. When you count in the orbital, you see that atom already has 6 electrons. Right? But when you count in this region, you think about what are the geometry for the molecule. You count in the region of the groupers. You count in all the 3 bonds, 6 electrons as one group. Right? Sometimes you will have those single electrons because you have some of those problems. You are adding up those number of electrons, you get odd numbers. So no matter what you do, one atom will have odd number. Right? So then there is one single electron counting as one group. So this work is pretty good in this chapter. You just study that right now, but when you study some other chemistry, you will see that not always like that way. So then this is the way that the book will tell you to counting how many groupers. So I get this other way from another professor. I saw his lecture, and he said you can just count how many scenes. And then the scenes, 2 types of scenes. Either those atoms bonding to the center, or those lone pairs. So that make your counting very simple. So if I have this problem, I will forget about what the book said. I will use this way, just counting how many scenes. So scenes is either atom bonding to the center, or the lone pair on the center. So now this is our center. Now when you talk about those geometry for the electron or for the atom, you don't have to worry about those terminal atom. Right? So this is our center atom, and how many scenes? One lone pair is one scene. One atom bonding to the center atom is one scene. No matter you have a double bond bonding to 8 or triple bond bonding to 8, if you use the other way, you have to see whether you have triple bond, double bond, you still count as one group. Right? So 1 scene, 2 scene, 3 scene. And then that means for this center atom, we have 3 groupers. So that's important. Once you identify how many groupers of electrons, and then you will be able to decide what will be the geometry, what will be the best geometry in this chapter for these 3 groups of something. Now these 3 groups of something, in this example we have 2 atoms, 1 lone pair. For some other problem, you might let all the 3 groups might be all the 3 atoms. So you will have all those different possibilities. But right now you just be able to count how many scenes. Okay? So then once you have how many scenes, and then those, if you think about only the geometry for those something, those group of electrons, there are five geometries. And then 5 geometry, probably this, what do you see in this, this slide? And in reality, some of the larger molecular might have more than 6 something on it. And then some of those simpler molecular like HCl, they don't even have a center, then you probably even have like less than what we said here. But in general, so these 5 possibilities is the most general. So this, all those like those orange or the yellow one represent the center. So one center here. And then on the center you have 2 groupers on the first one. So then what is the geometry for that 2 group of something? Linear. Just spread out as far as possible. One on the east, one on the west. The angle between these 2 groupers perfectly 180, but depending on the situation, maybe not that perfect. Then if you have some problem like what we saw in the last example, we counted that 3 groupers of electrons on the center atom A. Now what are the geometry for that 3 group of something? So roughly about this geometry, the sort of the trigonal planar. Trigonal means triangle. Planar means plane. Which means all these 3 groupers roughly evenly triangle, and they are on the same plane. If you have 4 groupers, and your geometry will look like this. This name called the tetrahedra. And then those angles here, they have different shapes, different angles. And then those angles here you hear is perfect angles, but depending on what you bond into. You might not exactly have 120, you might not exactly have 109.5. Right, so then if you keep going on, if you have 5 groups of electrons on your center atom, you have this geometry for that 5 something. That 5 something, you have this 5 corner here. And maybe 5 atoms, and maybe 4 atoms, and 1 lone pair, and maybe 2 atoms, 3 lone pairs, so all those possible. So now what is the geometry for this? For this geometry right now we have here, we call that trigonal bipyramidal. Trigonal again means the center or the middle part is triangle. Bipyramidal means we have 2 pyramids. The top pyramid, the bottom pyramid. The last one, you have 6 groupers of electrons on the center, and the name for that is octahedra. So this is the 5 very important geometries. So let's emphasize here. And this is the sort of the electron grouper geometries. So electron grouper geometries, that means you draw the Lewis structure, then you decide how many groupers on the center atom. If your molecule is simple, only have 1 center, you just have that. If you have more than 1 center, 2 center, you are counting for each center. Right. So the angles is right now the angle is perfect angles. That you might not have those perfect angles depending on what you have bound into the center atom. So the first one called the linear, which means once you draw the Lewis structure, you will have 2 groupers of electrons on the center. And the second one, so here the so-called trigonal planar, that means 3 electron groupers. And this so-called tetrahedra, which means 4 electron groupers on the center atom. And this is the 5 electron groupers. It's called the trigonal triangle. These 3 triangles. Bipyramidal, which means pyramid on the top, pyramid at the bottom. So you have 2 pyramids. And this is the octahedra. Octa probably confuse you. Octa means 8. But this electron grouper you have is 6. You have 6 corners. So that's a confusing name. Octahedra means you will have, you see this, those solid line here. So this geometry, if you imagine that geometry just by imagining or view this solid line in this geometry, you will see that you have 8 faces. So that's the name comes from. So if I highlight this is 1 face on the right on the top, and you will have 1 face on the top in the front. and then you have one face on the top, on the left. You have one face, that one, on the top, in the back. So 4 faces on top, 4 faces at the bottom, so they all together have 8 faces, so therefore the altogether. Alright, see if you get that simple idea used to decide the electron geometries. When determining electron geometry, what is important? Well, actually, not that difficult. Okay? When you determine the electron geometry, only consider the center.
So it's A.
You can use the one that about 29. So we'll start on 21. Alright, so now if you can decide what will be the electron geometry. Remember what I said, the electron geometry only have that 5 geometries, depending on how many group of electrons on the central atom. Electron geometries minus the linear minus the trigonal planar right, and then the other one is the trigonal okay, so that's depends on how many electron groupers you have. So you have 2 groupers, it will be linear, 3 groupers will be trigonal planar, 4 groupers will be tetrahedral, and 5 groupers will be trigonal bipyramidal, and 6 groupers will be that. So now what do we mean by this? This is pretty much either atom or lone pairs. So those numbers, just counting how many atoms or atoms bonding to the center, and plus how many lone pairs. If you get 2, and then those 2 car guys will be linear spread out. If you get 3, you will trigonal planar spread out. If you get B. Everyone read B? So we talk about this oxygen here, right? So right now this oxygen, B is right, the electron geometry is B is tetrahedral. That means you need to find out there's 4 something bonding to this O. So right now you have this atom here, that is this one atom. There's another atom here. And how we find a 4? We have very good, we have 2 more here. Okay? Remember the first question I tell you? If I give you the model like this, even though I did not draw that, or you did not see that lone pairs, you don't show the lone pairs for those geometries, right? Right, so once you adding on these 2 more pairs here, so this will finish that loose structure. Once you have the loose structure out, you will see how many atoms or lone pairs on the central atom. For this problem, we have more central atom. Now, when we talk about the geometry, you will talk about it 1 by 1. For this one, so we are not talking about the geometry for these 3 atoms. We talk about this geometry for this 4 group of something, for this chemical bond here, for this chemical bond here, for this lone pair here, this lone pair here. What is the geometry for this 4 something? This 4 something, that means this one will take 1 corner of that tetrahedral, this one will take another corner of that tetrahedral, and this one will take another corner, that one will take another corner. And obviously the perfect geometry of the tetrahedra is, the angle between this bond is 109.5 degree, and the angle between this line and that long here is 109. But that is ideally. So when you have like those something not all the same, and your angle will be a little different, not perfect 109. But right now at least you will get the name, even though the angle is not perfect 109, so still kind of looks like a tetrahedra. So we still call them a tetrahedra. Alright. So once you have this electron geometries, which means you have not really worried about how many lone pair you have, how many atoms you have, just counting them all together, have 5, 4, or 6, or 2, and 3, you get these 5 geometries. And then you decide the supermolecular geometry. Molecular geometry means you just like what we saw in the last some of those examples. You forget about those lone pairs. Just imagine what it looks like for those atoms. And now if you don't have any lone pair, if lone pair, let's see, if lone pair equal to 0, or no lone pair on some atom, so then we're going to use some of those abbreviations. So this molecular geometry, we'll call that Mg. Okay? And then the electron geometry. See here, the electron geometry, and you can call that Eg. So once you decide the center atom, if there's no lone pair on the center atom, then Mg equals Eg. Right? So then your Mg equals to Eg. And that means your molecular geometry will be one of these 5. Otherwise, if you have lone pairs on your center atom, and you are going to get something like from these 5, when you get something from these 5, you call them derivative. So let's see, if besides these 2 different geometries, 2 types of geometries. One is Eg. Let me use my abbreviation again. So this is our Eg, and this is a file view of those Mgs, Egs. And so this, you can see will be same if no lone pairs. If you don't have lone pairs on the center atom, then this will be the same. And this is exactly what we see in these 2 pictures. So here, so this side representing the Eg, which means you have the center atom, and you have those kind of electron cloud. You don't have the atom bonding to that. Just, some of them maybe have atom bonding to that, but we consider them all as that. Now here, you add in those bars, that means they really bond into the atom. Okay? So if all those corners were taken by the atom, so therefore you don't have any lone pairs. And then you have this 5 molecular geometry. Okay? But in this chapter, we are going to see plus 6 more. Plus 6 more, that is sort of the, these are derivatives. Okay? That means you are starting from 1 to 5, okay? And then depending on you have atom or you have lone pairs, you are taking some corner away or reserve one corner for the lone pair. Now what left over will be those Mg. Obviously, if you take one corner away, then Mg will be different than these 5. Right? So very simple. Just so for example, this 3, this tetrahedra is already here. Is a geometry. which means you see some of those like methane and ammonium ion, and you draw the Lewis structure, you count in how many electron groupers on center atom fall. And then for methane, which is CH4, which means you have carbon in the center, and you have 4 H bonded to the center carbon, and you don't have any lone pairs, so therefore your molecular geometry is also tetrahedral. But if you have some other molecular, and you draw the Lewis structure, you have 4 groupers, but one grouper is a non-bonding pair, lone pair here. And then you only have 3 atoms bonding to the center. So then your electron geometry is still tetrahedral because electron geometry referring to all those groupers on the center atom. So you still counting that as one corner, and then you have these 3 corners, so altogether for the electron geometry, you still have the tetrahedral. But if that one corner don't have an atom, it's kind of a fluffy cloud, and you're counting what is the geometry for the atom, so that corner don't exist anymore. So what are the geometry for all those atoms, kind of those solid? And then here 1, 2, 3, we call those kind of geometry trigonal pyramid, or trigonal pyramidal. Pyramidal comes from the word pyramid, by those Egyptian pyramid. And the last one, let me erase what I write. So this one, both of these two called the derivatives that come from that one of these 5 geometry. The last one is example for the last one is like water. So you draw the little structure for water, and you have O, and bonding to H, 1 pair, 2 pairs, so 2 lone pairs on the oxygen atom. Now this oxygen atom can be represented by this red. So now what is the geometry for this 1, 2, 3, 4 group of electron? Tetrahedral. So now what is the geometry for these 3 atoms? So obviously when you consider the geometry for the atom, so the electron, and you can omit them. So then the geometry will be the band. And this is the band from the tetrahedral. Alright, so you can have more. So you have this 5 geometry here, and maybe the same as, you might get these 5 that will be the same for this electron geometries, but your molecular geometry, maybe not this exactly 5, depending on how many lone pairs on it. If you don't have any lone pairs, so this one you get the same. Otherwise, you might have like this, and this obviously looks different than the tetrahedral. So then, if you have those lone pairs, and you have to think about where to put them, where to put those lone pairs. So we have these 5 geometries. For all that other 4, except this one. For the first pair, for all the other 4, for that one we don't even consider having lone pairs. And only for the other 3. For the other 3, the first pair, it doesn't matter where you put them. The reason is, if this is our center, and I have like one group, another group, of these 3 groups, and all these 3 groups are equivalent. They evenly spread out, and no difference between which one is which. Tetrahedral is similar. And then this octahedral is also similar. Now this trigonal biopyramidal is 5 group or something. And even though it looks also similar, but when you consider how far are those away from each other, so they are not exactly the same. We classify them into two types. So this one, that one, you can see from this picture, called the axial position. And then this one, axial position. Let me just highlight this one. I highlight this 3 in red. So this in red is equatorial, like the equator of our Earth. Alright, so believe it or not, this the space or the angle between those equatorials is larger. Which means those equatorial positions, the equatorial corner is a little bit like have a little more room. So those guys has more rooms. And one simple reason is you can see the angle between this one and this one. So angle between these two equatorial is what? And triangle in like one circle. Trigonal plane, the angle, perfect angle between one of those pairs, so how much?
Well, you're asking for the angle?
Yeah, as with the angle. So the angle here,
I would assume 120, right?
120, right? Because a whole circle is 360. So you divide even by 3 is 120. Alright? And then the angle here, what is the angle? What is the angle from this one to this one? 90, that's perpendicular. So that's one of those main reasons. So the reason is why those equatorial has more room, but the angle between them is even more. Right? And then you know those long pairs. Long pair only bonding to one nucleus. Right? So the bonding pair, like this one pair, maybe like that one, but it's so they like bonding to two nuclei. So you have one nucleus here, one nucleus here. So this bonding pair is like attracted by two centers of positive. Okay? If you have a long pair, that is only attracted by one center. Less attracted, that means the electron can fly out. So that means long pair take more room. Naturally, where it has more room, long pair will go to that place. Right. So for this kind of geometry, your first pair you don't put on the top or on the bottom, you put it here. And even for the second pair or the third pair. So for this geometry, for all the pair of non-bonding pair of electrons, just put on the equatorial, but there is more room. Right. So then for the other geometries, the first pair where you put doesn't matter. Then for one geometry, so where you put the second pair matters. The geometry is this overtaker. Okay? Your first pair, all these 6 corners are the same. Okay? You design the angles. Yeah.
What is a lone pair again? How do you know if it's a lone pair?
How you do the long pair?
Yeah.
Okay, let's say we draw the Lewis structure for water. Okay? The water is H2O, so I draw O. Right? H2O. And then you have H. Right? So that's the first step. Then you will see how many electrons available.
You see 2.
6 from oxygen and one from each H. So altogether you have 8 valence electrons. Right? So then you're going to distribute. Okay, so remember what I said? You first glue them together by putting one pair between the atoms. Okay? And then you complete the octet. So hydrogen don't need octet. So therefore you finish for both H. Only one you need to consider yet is O. You just take a break. You know what I said? Okay? So you already have four electrons on it. So on this one, you already have 4 electrons on it, on this structure. Right? Okay, you have 2 bonds. So then you will calculate how many left over.
Which is 2.
You have 2 pairs. So you have 1 pair, 2 pairs. So then you then still have to make sure your sample, the one you consider the last, has also octet. Okay? Now for this example, that's good. You put all those 2 pairs left over on the O, so you have 4 pairs, so that makes O has our test, so therefore you finish. And then you will see, so this dash, so sometimes we also call them a line, right? Is a camera bond. And this represents two dots, or two electrons. Right? That two electrons is called, that is our bonding, bonding electron. Right? And this is one long pair. Okay?
Yeah.
So that is another long pair. Right? So long pair, arrow P, right, equals long pair. Right? So that means you have two electrons. Long, that means these two electrons is only on this O. Now these two electrons here is attracted, or it is on two nuclei. So on this nuclei, on this nucleus, also on this nucleus. So therefore it's attracted by more positive. So therefore it's more confined, more limited. And those lone pairs only attracted by one nucleus, so therefore it becomes kind of fluffy and take more space. Alright,
So is that considered tetrahedral then? No.
you the electron geometry for the water,
Yeah.
still tetrahedral. So you have here, this five geometry is very similar for the electron. So no matter what you have, even though you know that's not perfect, but we just say when you have two, yeah.
So for geometry, it would be tetrahedral, but for molecular geometry, it would be a linear?
Well, it depends. You think about, let's say you have a tetrahedral, this looks like this. So this is tetrahedral. Okay? Now you have four corners, which means these four corners will be used for these four groupers. One grouper is here, a bonding group. Another group here, another bonding group. So you have four groups of electrons. So you will see, you start with this geometry, but you have to take one corner away for one pair first. And you have two pairs, so therefore once you take this away, you think about taking another pair, another corner away. If you take this away, you get a so-called trigonal pyramids, and then all the other three corners are still the same, so you can take any corner away. So as a result, you can take this corner away. Example, you can take any two corner away. I can take this corner away. I can take this corner away. What does it look like?
A bent?
A band.
Oh, so we just gotta go off the we have to go off the EG.
Yes, yeah. Step by step.
Yeah,
Okay?
okay, that
You
makes
have to
sense.
be able to draw the little structure. You have to be able to identify how many lone pairs, how many atoms on center atom. And then you will see what is the geometry for the electron. Like how many lone pairs you take to the corner away. So usually you take any corner away, but for that trigonal bioperimeter, be careful, you always take the equatorial. And for this guy, you take the first corner, you can take any corner from, for example, from bottom. And second pair you can take, you must take the opposite. Right? Any other question?
Why do you have to take them away?
Because they don't have atom. When you consider the molecular geometry, you can imagine when you consider molecular geometry, you don't have to pay attention to those corners that don't have electron. Even though that will influence you. If you don't have electron, don't have atom on that corner, that might make your geometry not that perfect as this five geometry. Right, so these five basic geometry, we start with these five, we call them electron geometry. And if you see like the electron geometry will be these five. Okay? And so then your molecular geometry, maybe these five, maybe the other six. If you don't have any lone pair on the center atom, then if you have this geometry for your electron, then your molecular geometry is also the same. If you have like lone pairs, then depend on which one you have lone pair. You have lone pair on this one, have lone pair on this one, and also depend on how many lone pair you have. So we have 6 more than these 5. And let's consider them, okay? So we will start with this molecular geometry with these 5 basic, which means you have these 5 geometry, that means you don't have any lone pair on the center atom. Okay? And now let's review the name, right? So first one is called linear. Get it? So that's linear, obviously very straightforward. And this one, the second one is called the trigonal planar. Be very careful, planar, which means all these 4 atoms here, which means on the same plane. Okay? So I think next week I will give you the model, and I want you to make the model, make those molecular. Usually, I see like from my previous class, and you will make it easy mistake. And a mistake, you will see that sometimes you will try to make that trigonal planar, but the middle one kind of like popped up. Right. So that you will call the trigonal pyramid. And so then this, the number 3 here, are our tetrahedra. Tetra, that's good, because tetra usually means 4. And tetrahedra, and this one, that means you have 4 groups on the center, and this one, then you have 5 groups on the center. So this is called the trigonal. The trigonal comes from these 3 atoms. So this atom, this atom, this atom. You call them equatorial. So these 3 atoms, they produce a geometry that looks like triangle. And triangle, then in other words, pyramid, you can imagine pyramid, right? Yeah. So you have the pyramid depend on the base. So this is the pyramid, right? So if I make a connection here, and I wind it back, obviously you cannot see that. So this red line representing one pyramid, where the other pyramid? That's not it. So therefore we have the bi-pyramid. Right, and so then this one, that means you have 6 electron groupers on the center atom, we call that octahedra. So again, octa, that means you have 8 corners, because octa means 8. Octa means 8. You don't have 8 corners, but you have 8 faces. Right, so now let's consider those derivations. So how can we get more geometry for this from this slide? That depends on what? So see 5 here, and 6 here. This 6 we're going to get, it will somehow come from that 5. That depends on what? Depends on the lone pair. Now what we consider is 1 lone pair, 2 lone pair, no, again the pair. Okay? Just think about 2 electrons counting as 1. So 1 pair, 2 pairs, 3 pairs. For this guy, they're already very simple. You don't think that at all. So you just think there's no like those lone pairs. So we skip this one. Now the next one, you possibly can have like a lone pair. You possibly can have one lone pair. So if you have 1 lone pair, that means right now you have all the 3 corners. You see that, you show that. But if you consider the molecular geometry, if there's 1 lone pair, which means 1 corner, as Don was asking, you have to take that away and reserve it for the lone pair. So you can still imagine if you use like very like gentle picture. That means you still have those electron cloud there, right? But those really not really the geometry for your atom, because those atoms are really some matters, and you can. So they take a room, they have mass, right? And electron is also have so electron also have like mass and take a room, but not so like important as atom. It's only like very small mass. You agree? Right. So therefore we have this geometry. Now this geometry. Even though I show this red dot, but you don't have to consume the red dot. And what do you think of this name for this reaction? Linear? Band, right? Yeah. Yeah. So that makes sense. That's band, not linear, right? Right. So now we will go on and consider one lone pair for this geometry tetrahedron. Very good. Trigonal pyramid, right? So what you get is this. Everybody see that? Okay, see the difference? I will think about it from this geometry. I will take one corner away and reserve it for the long hair, right? So therefore, I only have like this 3 corners now. So this is not the corner actually. This is still the center. It looks like for the molecular geometry, it looks like a corner, right? And then what do you call this geometry? This geometry will call it looks like a pyramid, right? Looks like a pyramid. And then what kind of pyramid? You can have different pyramids depending on the name, depending on the base. So some of the pyramid you call that square pyramid, and some of the pyramid you call that trigonal pyramid. Right, now let's go back. Let's go on. Let's think about this from this guy. From this guy, we still consider only one long pair. Let me read what I draw on that. And what do you think? If I have one long pair on this center atom, where am I going to put it? Let me circle like different colors. So this red one. Okay, now let me ask you, where are you going to put that? Are you going to put that on the red one? Or are you going to put that on the green one? You have one long pair. Where are you going to put that?
It's going to be a seesaw.
That means you get that by putting that long pair. I thought you want to see, but you kind of change your mind because it's.
Yeah.
So you put that on this place, on those red circles. Any of these 3 red circles will be fine. But that's, as we said, called the equatorial, they have more room. Why do you want to put that? They have more room because those long pairs, they take more room. Right? So now you just imagine you are going to take one of those away. Right? So what we did is kind of take neither of those away, but we can take this away, then we rotate. Right? Figure that? So if you take like really one way from that, you will not get that big picture, but you can rotate it a little bit. So that's what you get. And this geometry called the seesaw, the kind of those little toy you see like in some of those playground. Alright, so then let's go on with this guy. Right? So right now we have this 6 corner. Now imagine this 6 corner, 5 of them is atom, and one group is long pair. Okay? So where are you going to put this one long pair? Actually, this one, all the same. So you can still imagine this one. Let me circle that. Like you can imagine like it's still the same. So this one and this one, that's not really axial, right? But no difference. Because you flip them, then they can all become the same.
So all of those angles are the same?
All angles are the same. Yeah, all angles from here to here. How much? Perpendicular, right? Because this is the plane, this up and down to this 90. And here, also 90 because 490 is 360. Yeah. So then you can, for the first pair you can take anyway. Right? And what we did is it looks like we take the bottom away. Okay? So what we get is this structure. Understand? You can take any away. You can take any way you rotate, you get this.
I thought you couldn't take the axial.
We take the equatorial away from only for this. We only take the equatorial away from for this. For the others, for the first pair, you can take any away. Okay. So this one you take the red away. That's called equatorial. Now this one you don't have those names actually. All of them are the same. So you take this away, and if you take the top away, you flip over, that becomes this. And this one also looks like a pyramid. Okay? So all the pyramids, like the Egyptian pyramids, have very like pumping top, and they have different base, right? So this is called a square pyramid. Alright, so you go step by step. Now once you have this four, okay? And this four you get by have like one long pair from that five. And then you can start from this four, you probably not start from this, you start from the other three, and you take one more pair away, one more corner away, that means you have two long pairs, and you get more geometries. Right? So now let's think about it. We have two long pairs. We actually ultimately we still starting from the top. Right? So now let's see, we don't have any like that. We also not going to consider like this guy. Okay? So we don't consider this guy have like two long pairs, which means this guy. Okay? Now you think about you have another pair of non-bonding electrons, and that means altogether have two from that one, and you have one from this one. Okay? So you have to take one corner away from this one, and so therefore you altogether have two. And imagine this is still our center, so you don't consider that is a corner, don't take it that way, right? So keep that, and these three are still equivalent, right? So one here, one here, one here, and they still spread out and the same, okay? So what you do, you can take it any one way. So again, it looks like you did not take any one way, but you take this one way, then you rotate that little bit, you get this. So now what do you call this? What do you call this geometry? A band. It's not, it's not linear, so this is band. Alright, so then you are going on with this one. So right now this one you get by taking one corner away from that, you get this seesaw. Again, you're starting with something molecular, you get the electron geometry like this. But that electron geometry, from that electron geometry you have five groups, you get this. If you have two long pairs, so you take one corner away, you get this. Like continue from this one, where are you going to take? So what you do, you're going to take, again, you're going to take those equatorials. Okay? So what we did is you can take any one of these two away, and you get this. And this name kind of easy, it looks like the letter T. Okay? So therefore this is T-shaped. Okay. Alright, so now you starting with like this geometry, which means you draw the little structure, then you identify the center atom has altogether 6 group of electrons, but in that 6 group of electrons, you have two of those long pairs, two pair of non-bonding electrons. So what you do, you take one pair, and you get this square pyramid. Now the problem, you're going to take the second pair, right? Or you're going to put the second pair on this structure, right? Now you have a difference, right? You probably don't want to put it here, right? You want to put it here. The reason you don't want to put it here, if I draw like this guy here, right? So this is our long pair here. I take a lot of room, okay? If you put it here, okay? So a lot of guy here, so they will get too close. So where you can put that? You put it on the top. Right, so you get this, right? So even though in this structure we don't have that anymore, so we're supposed to have like we have two pairs of that, right? Long pairs. But for the molecular geometry, you don't have to really worry about that so dramatically. Sometimes that still influence your perfect shape. And then what we call this, we call it a square planar. So just pay attention to all those names. Square, which means this 4 atoms in the corner is a square structure. Planar, which means they are really, really flat. Alright, so then I think we'll have like one more possibility come from this. Okay? And we are not going to consider that 3 pair of electrons on this one, 3 pair of electrons on this one, but we can consider, I mean we have some of those examples. that has 5 electron groups on the center atom, but 3 lone pairs. So if you have 3 lone pairs, so you will take one more corner away, which means one more of the equatorial away, so you get that. And then, so that's all together. If you count in this, so you know here we have how many? And obviously we have, well, 8 more than that 5, right? But we said we won't have 6 because some here is kind of duplicate, right? So this not even not exactly the same band, but we just give them the same name. So this band here, and that band here, even though precisely not the same in terms of angles, that angle is about 120, this angle is about 109, but we just consider them as the same geometric band. And then this line linear is already here, right? So you take 2 more away, so you altogether have 8 here, so you have 1 duplicate, and this is already very duplicate, so you have 6 more. Okay? So 5 basic, right? And then plus 6, we call that derivatives. 11 geometry, so there's few more names. 11 names. Right? So then the procedures, I think you emphasize the procedures, and that is important, but I think you will see those procedures once you get a few practice. So first, and what you do is draw the little structure, right? And then you decide the total number of electron groupers, which pretty much see how many atoms bound to the center atom, how many lone pairs on the center atom, right? And then you will decide what are the geometry for the electrons, and just any of these 5. And then you decide how many lone pairs. You have 1 lone pair, take 1 corner away, and so then you remember what corner you can take away. For like some of those 5 geometries, you can take any corner away, the first corner. But for this trigonal bioperimeter, remember take the one from the middle. Right. So then you also remember those angles, and so that's about that. Well, I think this is kind of duplicated one slide. So this is just different way to organize those informations. And again, we will organize them according to the electron groupers, right? So how many electron groupers, how many possibilities do we have in this chapter? There are 5 possibilities, right? So this slide shows you 3 of them. You can have like 2 electron groupers, 3 electron groupers, 4 electron groupers. And then you will see you can have 5, you can have 6. Right? And so that's it about that. So I will quickly go through that, and you can read this table by yourself. So let's spend some time on some others. Probably good.
Are we going to tell the angles of it for the test?
Yes, you have to memorize those ideal angles, those. All right, let's do a practice. Okay? And I think in the procedure you will see, like for some problem, if there's a red structure, that means you have more than one possible way to represent your molecular root structure. You can use either one of those. So for this one, you want to determine the molecular geometry. So you first have to see the procedure. So I'm going to emphasize that. And so I will first draw the root structure. Okay? When you draw the root structure, first you identify what is the center. Right? So A is the center. Okay? And then I will put an O, and O, and O like that. So I have 3 O. So the second step, I will count in how many electrons. So altogether, I have 24 electrons. Everybody agree? Where does the 24 come from? So this one will give me 5. So this one will give me 18. 3 will give me 18. Then 1 negative will give me 1. So we have 4, 6. Okay, so then I will first do like the group. Okay? And I will finish the octet for the terminal. So I finish the octet for all the 3 O. Then I will counting how many U's. So I already have 24 U's, so 0 left over. So now I have to worry about the center. Do the center need an octet? So now what do? We can just take I can take like a 1. Okay, I can take a 1. So let's see from that. Right. So I will take that away and put it here. And this is one possibility. You can take it from the left one, you can take it from the bottom one, right? Right. So this is one of the 3 important resonance structure. Okay. Now you can use either one. Okay. The other one I will use a line like this. So you have A, R1O, and single one O, through here, and O here. You can use either one. Okay. So now let's use, for example, use this one. Okay. Go to the next step. So this is our root structure. What you want to do is decide what is the molecular geometry. Okay. So let's counting how many electron groupers. Number of numbers of electron groupers. On N, when N is our central atom. And so now any idea on this N, how many electron groupers? Right, 3. What are the 3? So we think about either the atom bonding to the center or the lone pairs. What make out the 3?
2 single pairs and then the double pair.
Yeah, we can think about that. That's what the book is telling you. Okay? If you think about the atom or the lone pairs, okay? So here is very simple. Just if the atom or the lone pair, for either case, just consider that as one something, as one electron group. Okay? 1 atom, 2 atom, 3 atom. Do we have any lone pair on N? No. So therefore we have 3 electron groupers. Got that? So step by step, 3 electron groupers tell you the EG. EG is what? What is the EG standing for? Electron geometry. Electron geometry. Yeah. So what is the electron geometry? Only these 5 possibilities. What is the electron geometry for this molecule? You can see called as trigonal or planar. Alright. So now from this, we are going to think about what is the molecular geometry. I think one like pattern you probably already remember is if there is a 0 lone pair, then if there is 0 lone pair, then your MG and EG is the same. Okay? We don't have any lone pair, therefore the MG and EG are the same. Right? So your MG is also trigonal planar. Is that simple? So what is the angle between those bonds? Between those atoms? 120 perfect. Okay, 120 perfect. Even though if you only think about there is only one geometry like this, or only one structure like this, so you have a double bond here, single bond here, so double bond will take more space, so you kind of might squeeze this bond angle less than 120, but remember this is only one possibility. You can have this possibility, that possibility. So in reality, the best structure for this ion is neither of those bonds is a single or double. It's just kind of somewhere between single and double. So all the bonds are the same. So if all the bonds are the same, no single, no double, so therefore it's perfect angles, perfect line plane. Get that? Right. Two angles. Okay. Here is 120. Here is also 120. Here, also 120. Okay? You probably see, you're not right, because it looks like this is the double bond here. Right? But this is not really the all structures. This is only one of the three structures. Right, I think you get it, right? If you have some pattern, and ask me right away. Okay, you have some comments. You find some patterns, and you're not sure about that, and just so that's sure that. All right. So that's this example show you the procedure. Okay. Show the procedure. Now we do a practice. Okay? So this will be on your 2024. So you still use the same standard for the 12-9. Okay. So tell me what is the molecular geometry of the MG? Okay. Molecular geometry, remember we call that MG. Okay. MG. Is A, tetrahedral. Very good. Okay. Any question? The loose structure is C in the center, right? And CL, 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 and CL. Right? So how many electrons we have for this molecule? 32. Right? So 32. You first do a group. Right? Then you complete overtake. So each CL needs like 3 more pairs. And you just put 3 more pairs on each CL. Okay? Then you leave that last atom with the carbon you did not consider yet. Then you see, you take a break, see like how many electrons you have? 32. How many electrons on this? 32. So you have 0 left over.
That's it, alright.
And then you still want to make sure that the center, if the center needs overtake. Okay? So even though we kind of going back and forth, sometimes you give them overtake and sometimes you give them back in some other theory. We'll talk about the bond polarities. Okay? So then, so you will see that that's it. So this carbon has a 4 chemical bond. That means you make that overtake. Right. So then you have the next step is to decide how many group of electrons. Right. So once you have the loose structure, what you decide is how many electron groupers on the center. How many electron groupers? 4. This time, these 4 also come from 4 what? They come from like a 3 lone pair, or 3 atom, 1 lone pair, or they come from what? Just 3 atoms. Just very simple. You can use what the book said, or you can just see on the center atom how many atoms bonding to it. No matter if you use double bond, triple bond, there are 4. Now you'll see how many lone pairs. Right? Adding all of them together. Counting how many atoms bond to the center. How many lone pairs are there? Okay? There's 4 atoms and 0 lone pairs. Okay? So therefore your EG will be this tetrahedral. Right? Now one pattern you probably already remember is if you have a 0 lone pair, your EG same as the MG. So this is an example, right? Okay, now more practice, that means you want to emphasize the bond angles. So if I have this molecule, I want to see what is the molecular geometry without bond angles. So again, just procedure. First you draw the loose structure. So loose structure, I will put a P center, then CL, 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 right? So usually I will not put the phosphorus in the center, but use like the center, right? So what you do, you count how many electrons we have. How many electrons we have available? 26. Okay? Any question about 26? 3 times 7, 21, right? Then plus 5 from phosphorus, 26. Okay? 1 line, 1 line, 1 line. Each 1 line representing how many electrons? 2 electrons. So right now we have 6 electrons on the structure. Okay? Now let's complete overtake. So that makes it Crowley overtake. Okay?
Don't you need a lone pair on the P?
Okay, good. So let's see, probably we need a long pair. So now we have all the CL has overtake. Right? Now you just take a break. So you will leave the last atom like you did not check yet. So how many electrons already here? 24. So therefore we have a long pair level. Okay? So you just put the level electron as a pair on the center. Sometimes, even though you put that level over on the center still don't have overtake. If the center needs overtake, let's do something else. Like what we did in the double bond, right? And then in this example, do we need to do something else? Probably don't do anything else, because this phosphorus has 1 pair, 2 pairs, 3 pairs. So that has like 4 pairs, all the head,
This
right?
baby will just drop it.
All right, so then what you do, you are counting the number of electron groupers, okay? Which means atom bonds to the center plus lone pair on the center. Get that? So this is a very easy way to count how many electron groupers on the center. Okay? So what is our center atom here? Phosphorus. How many atoms bonding to it? 1, 2, 3, 3 Cl. Okay? So therefore, so let's continue. We have 3. Okay? 3 plus what? 1 lone pair. 1 lone pair. Okay? So 3 plus 1. So you have 4. Okay? Now 4 electron groupers. Okay? So we have this is 4. So that tells you the very good, right? You kind of confused, very reasonable confused. So I will call this not the electron group, call the electron geometry. Okay? Now electron geometry. So what is the electron geometry if you have 4 groupers? Tetrahedron. Okay? So you start with tetrahedron for your electron geometry. Okay? But you have 1 lone pair. So any lone pair you have on the central atom, that will make your electron geometry, molecular geometry different. Okay? So therefore, if you know that electron geometry is tetrahedron, your molecular geometry for sure will be not tetrahedron. Right? Then you just find out you have to take like 1 place away for the electron if you have 1 lone pair. Okay? So what is the molecular geometry? Trigonopyramid. Trigonopyramid. And so then you want, so that's the geometry name. Now you want to see like what is the bond angle, right? So what is the bond angle for the perfect tetrahedron? That's a few names, few angles, like 80, 180, or like tetrahedron, yeah, trigonal pattern is 120, right? So tetrahedron that means become more crowded. So the pattern pretty much as the number of electron groupers increases from like the top to the bottom, your angle getting smaller and smaller, right? Here is what, 120, 180. So then you write that. So this is 180, right? And here we talk about the more perfect, right? So this is 120, and then this is about what?
90.
Okay, right. 109. And here you will have those, so this one you have 90. And also like 120, right? And here they all become 90. You can see gradually, on average, so the angle getting less and less. Because they become more and more crowded. And here you have 90, then you have 120. Then here you don't have 120 anymore, they all become 90. Alright, so then what is the bond angle? What is the thing? What is the bond angle? 109. It will be perfect 109. It's less than 109. Yeah. Very good. Why is less than 109? Because the electron take more room. Because the lone pair take more room. So they take more room. So you then make the angle become less than 109. So you see that? Right? So you will see this. And this will be that's what the very good picture to tell you this lone pair is the only bond to one nucleus. So all those other pairs in between 2 nuclei, so therefore they are more limited, and they take a less room. All right. So now you do a very similar practice. I think that's a very similar practice. The same as the last one. Also, if this question did not ask you the bond angle, what is bond angle again? That's the one, man. Very good.
C? Was it C?
Yeah. Right. So this not really looks strange. Just telling you this end is our center, Right? So draw the little structure. Right? All the little structures in the center.
do you know the end?
That's the best structure. Otherwise you can put a tool in the center, then you will see that, or you can put a CL in the center, you will have a scatter. Right? CL, usually not center, because CL most stable is one camera bond. Right? If you put CL in the center, that means at least two camera bond. Right? The choice between N and O, N is less electronegative, so therefore you will put the less electronegative atom in the center. What do you think of that? C gets something right. That's not really the molecular geometry.
That's E, right?
It's E. Right? The band and less than 120. So that's about this.
And the double bond is on the oxygen.
Yeah. The double bond go on the oxygen, right? And you can see that. Right. So now let's do another practice. So I have ICL1 negative. So let me do the example. So this is CL. Okay, so this is one atom, CL. So this is chromium. So I will be the center, CL, 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 CL. Right? How many total electrons we have? 35 plus 1, right? Good. So we have 36. And we will make like the connection first. Right? And then you will complete all that. Right. So that's it. You first complete all the terminal, and then take a break. Okay? So how many electrons right now here on this structure? 32. So 32 minus 32. So we have 4 left over. Right? What do you do to the left over? On the center. You can put it any place. Just make sure you put it as a pair. Right? And so then you check do the center has, if you need overhead, do the center have overhead? And have more than overhead, right? More than overhead is okay for those large atoms. And I is good, because I is in the period 5. Okay? If the atom in period 3 and below, so that's good. So then that's it. And then we finish the loose structure. So what is the number of electron group? Very good. So 6. So 6, this 6 come from what and what?
The atoms are.
Very good. How many atoms? 4 atoms. Plus how many lone pair? Plus 2 lone pairs. Get that? So very simple. Once you get loose structure, okay? Even though some of those loose structure has resonance, you have more than one choice, but you can use either one. So you have a 6. Okay? So those information tell us what is our electron geometry, EG. Right, so that means is octahedra. Okay. Now octahedra is our EG. Now the question is about what? About your MG. MG that means you have to take the lone pairs. Don't consider the lone pair first, right? Right. So what is our MG? Square. Yeah, square pyramid, not a pyramid. You take one corner away from the octahedra, you get a square pyramid, and you take another corner away from the opposite side, so therefore you simply get the square planar. Right? It's very, very flat. That means all these 5 atoms, the iodine in the center, then have like 4 CL like in the 4 corners. Right? And what do you think about angle? The bond angle is, I think in this case, the bond angle is perfect what? Perfect 90. Alright, so that is the structure. Alright, now you do a very similar practice. So now we talk about some of those central atoms have more than octet. Okay, so everyone, let me see a quick practice. You can draw a root structure for this arsenic trifluoride. Identify the center atom, right? And how many electrons? Very good. So that's your root structure, right? Good. Yeah, very good. Very good, very good. I want to see everyone be able to draw a root structure of this molecule. What your root structure looks like. Very good. So then that's the root structure. How many electron groupers on the central atom? 5 atoms, no lone pairs, right? And then what is the geometry for the molecule? Number 5, but it's on the
And this one is C.
yeah, that's good. So starting from that. Counting how many electrons?
6. This is 7.
Very good, man. Yeah. So complete overhead for all the atoms. That is the terminal first.
Oh, yeah.
Okay, so what do we think? That's your structure. Okay. How many electrons? Okay, good. So then that's perfect. So that's called what do we call that geometry?
Trigonometry.
Trigonal biparameter. That's very good. You get it? You already get that one, right? That's simple. Get that? Okay, perfect.
I'm sure this is all we focus on. Drawing shapes.
35 plus what?
Guess how many of these questions?
How five? Okay, so the answer is 6.
AP questions showed up on this.
Because it's called the structure, So who is the center?
Quantum.
He is the center. Okay, now you draw it. Okay, as a center. I have 5 F. Okay, so then you make one line within then. So then you have each F have overhead without F in overhead. So adding 3 more pairs. Okay, so then the last one we do that again. How many electrons on pair now? So 5 times 8. 40. You already used all the electrons, right? So now, if I still want to compare, check that. Arsenic right now has overhead. More than overhead, because right now has 10 electrons, right? That's okay, perfect. So then that's our root structure. What you do next is counting the electron groupers. How many electron groupers on the S, on the AS? 5. And 5 means electron geometry is what? Trigonal biparameter, right? All right, so that's. So the answer is option C, right?
Yeah.
Now we talk about now is for some simple atom only have one center. So now we're going to see some atom has more than one center. So as I said, we will use this 11 terminology. For like a protein or like DNA, obviously because they have the sort of double helix.
You skipped one C already.
Really?
It's an H.
Yeah, sorry. So yeah, this one. Yeah. So try to do this one. Just click on that. Be careful, be careful. Let's see you get A or not. A, that means you can either get the trigonal planar or come from the tabular, right? If you draw the Lewis structure, and how many electron groupers, what is the center? Who is the center? You have 3 atoms the same, right? You can just put any one iodine in the center, and then you have. No, don't think about that. You go step by step. You just think about what is, this is your Lewis structure is right.
Yeah.
Counting how many electron groups on the center atom?
Well, I think of three, because I see three atoms.
No, you, on the center atom, you see what atom, how many atoms bonding to the center atom? Who is the center atom? This one, right? How many atoms bonding to the center atom?
Two.
Two.
So is there always one central one that you pick?
Maybe more than one center.
Okay.
There's always one center. So that if you more than one center, you will examine each center separately.
So you don't just count underneath there.
You don't worry about those like those really not center. You're just counting about the center first. So this is one center. Next problem, like this problem, you have one center here, and another center here, another center here. You have three centers. So now on this center, you will have one atom, two atom, right? Now you see how many lone pair on this center. One pair, lone pair. So one lone pair. So you have three lone pair plus two atom altogether. How many? 5 pair. So then, yeah, that's the easy way to do it. So now once you have 5 pair, you see those what I put there, right? So what is the electron geometry? 5 parameters. Now you want to take those corner away for the lone pairs. For this geometry, the super trigonal biopyramidal, you have two different geometries, two different corners. The top and the bottom for the axial, the three in the middle for the equatorial, and any lone pairs you put on the equatorial. So if you imagine you have one top, one bottom, three in the middle, and you put all the three in the middle, what do you get? Yeah, you put all the three equatorial as for the lone pairs. So one atom on the top, one atom at the bottom, one atom in the middle, linear. So I think that's good. What is the answer for this? Linear.
It's not polar.
All right. So let me just summarize what we did.
How many bonds would we connect?
Right.
Just think about it.
Everybody understand? This looks like good because all the I went like lines. And I do like this.
That one's missing one.
Yeah, okay, that makes sense. No, it means it has.
Right? And these three I.
Because positive.
Yeah, so that's the extra one I'm gonna.
How many electrons available?
So I was thinking positive.
22, right? The 22 electrons. And you just complete our test. Okay? So right now I have how many? 16. So minus 16. So I have 6 electrons left over. What do you do to these three? You will see that will become 3 pairs. So one pair here. Where you put them doesn't matter. One pair here and one pair here. Okay? All right. So just step by step. Lewis structure is so important. Okay? Lewis structure, and then you counting how many electron groupers, which means atoms. Okay? Let me just finish it like this. Atoms bonded to the center plus lone pairs on the center. Right? Right. So this is our center. How many atoms on the center? Bonding to the center? 2. Okay. How many lone pair on the center atom? 3. Right? So very, very simple. If you like don't like feel like some of those anxieties, you just there are 5. 5 means you have trigonal bipyramidal for the electron geometry. Okay, which means where I'm going to put this one group here, okay, one group here, and plus 3 lone pairs. All these 5 electron groupers. Perfect geometry will be the trigonal bipyramidal. Okay, and once you have that, so you have something like this. So this is our center. And so you have one corner here, and you have one corner in the back, and one corner is in the plane, and one corner goes up, one corner goes down. Now this geometry is literally special. What we call this axial, axial, and axial. Right. So what do you call this? By indicating by the 3 equal equatorial. Okay. Long pairs goes where? Goes equatorial. Okay. Right. So if you take all those equatorial way, take this one way from for one long pair, take that away from another long pair, take that away from the other long pair, what you have left over is what? Is straight. Alright, so now we talk about this molecule has more than one center, and this is one example of methanol. We're going to do like this lab measure methanol's weak property. Okay? So what you do, you first draw the root structure. Okay? And so let's make it very simple. These are root structure. Right? Okay. So how many central atoms do we have? And who are they? 2. Okay. Oxygen, this is one center. So what else is the center? Carbon. You have 2 centers. So you are going to use one of that 11 name to say what is the name for oxygen, what is the name for the geometry for the carbon. Right? You first decide how many electron groupers. Okay? How many electron groupers on the, so now let's see the table, right? We have a carbon in the center, you don't have to worry about those terminals, right? The carbon in the center, oxygen in the center. Now we see what is the number of electron groupers on carbon. 4? Okay. What are the 4? The 4 electron groupers on carbon that come from 4 what? 4 atoms. Okay? 4 atoms. Okay? So this is carbon. Okay? 1H, 2H, 3H bound to the carbon, and 1 oxygen bound to the carbon. And you only consider immediately you have this oxygen that considered as 1 atom. Right? So now how many electron groupers on the oxygen? What are that for? 2 atoms. What are the 2 atoms for this oxygen? This H and then what? The C. Okay? How many long pairs? 2 long pairs. Yeah. Okay. So therefore, let's say the carbon has how many long pairs? Have 0 long pairs. So the carbon has 0 long pairs. Okay. Right. So then, if you have 4 electron groupers on the central atom, what is the electron geometry? Tetrahedral. And I think one thing I emphasize this number 3 times I tell you. If you have 0 long pairs, your EG and the MG is what? The same. Right? So therefore, this molecular geometry for this part of the molecule is what? Tetrahedral. Not 4, tetrahedral. Okay. Right. So then you do the same for the other one. For oxygen, 4 electron groupers. But for this oxygen, how many electron groupers? How many long pairs on this oxygen? 2. So then you are starting with, if you have 4 electron groupers, no matter if they are atom or long pairs, what is the electron geometry? Tetrahedral. But the molecular geometry, if you have 8 long pairs, it will be different than your electron geometry. So therefore, you will see the band. Right. So then that's it. You can see like what are the angles, right? So the perfect angle for this part, the tetrahedral is again what? 109. Yeah. And then the angle here is also like 109, but both of them probably not a perfect 109. Right, let's see. So now let's see this one. I think I omitted some of the program. If you want to draw the root structure completely out, and you will see like this. So you have this carbon in the middle, so you have this O, and then you have this oxygen, then you have this H, so then you add like 2 more pairs, and then this will be our methanol. Right? So if you have this complete root structure, so in that structure on the left side, how many central atoms do we have? How many central atoms? 3 central atoms there, right? So now this problem is about what? Predicting the molecular geometry about the meter or carbon, this problem, so therefore I omitting that part, right? So that's should be very easy, because I think that if I give this kind of structure, then you have to make sure everyone has octet, if you need octet. Do we miss anything, miss lone pairs or something like for this carbon? I think for the carbon, we probably miss a lone pair for this O, but that's not the center, right? So you have a pair here. Okay, so you have two more pairs on that top O. You have two more pairs on that O, but we are not considering this O, so therefore you don't have to worry about those these lone pairs. So the question about this carbon, does this carbon have any lone pairs? If you put a lone pair, that means carbon has more than 8, right? All right. So what is the answer? For which one? For this C, for this carbon, the middle carbon, so this carbon not considered. The answer is B, right?
Oh, yeah.
All right. So now we consider this. So I give you this those problem like this. The first few problem, I still want you to practice draw the loose structure. So now I don't want you to draw the loose structure anymore. But you still have to review if you don't. You are not very good with that. So we have that two names, the EG and the MG. For this O indicated by this arrow. So what is the EG and what is the MG for that? The answer is E. Any question about that? Very good. So then you should be able to do those practice. Like those are very important in organic chemistry. So I will just go very briefly to see that. I think I draw one little take first. What that means, you're going to use the sort of the straight line. Those are straight lines. Okay? So if I draw something like that, that means that something is on the plane. Maybe on like the screen, or maybe on the paper, or maybe on the board. Okay? And so now we have some other notations. And if I have a solid wedge looks like this. So just kind of a triangle, and then you will just make it become solid. So this means out of it's out of the screen, out of the board. And then you have those hatched wedge. Hatched wedge looks like this. So that means it go retreating back into the screen. Right. So that's the conventions. And then you try to imagine, for example, this one I drew before. Right? So this X, if I circle in red, so these are in the screen. This is in the screen. Right? And this, there are two more X. There are two more X. This X is in what place? In the front or in the back? In the back. Okay, so that's very usual convention. This one in the what? In the front. All right. So you can get used to those. You do like more of those structures in like some other chemistry class. And similar for this SF6. And then we are going to talk about briefly about the polarity of molecules. Right? So the polarity of the molecules depend on a few things. And according to what the book says, it will depend on whether you have polar bond. The polar bond might come from the difference of electronegativity, might come from the uneven distribution of the lone pairs. Not only depend on that, it also depend on the molecular geometries. Geometry or shape are the same. So depend on these two things. It's kind of complicated. You can use different techniques to find out your results if you have the polar bond. I will show you I think on the lecture notes I have 4 different techniques. But I will emphasize only use one technique in this class. So then the polarity is really important for chemistry. Very straightforward is the polarity will affect the intermolecular forces, which is topic of chapter 11, and also really influence those reactivities. So when you start into chemistry, for example, you have that C and Cl and H and H. So because Cl and C have different electronegativity, then right away in the chemistry they will tell you this become a very active chemical called alkyl halide. So even though if you calculate the formal charge for both Cl and carbon is 0, but because electronegativity of Cl equals 3.0 and carbon equals 2.4, so there's a difference between these two numbers, and the bond between C and Cl is polar. So polar bond, that means you can represent this Cl with a little bit of negative charge, and you can represent the carbon with little positive charge, even though the former charge is 0. So therefore, as I emphasized before, you can use different ways to represent those informations. So then if you put it with some other chemicals in it, for example, water, and water has those F electrons on it, and water going to attack with that O on this carbon. Then the chemical reaction happens. You can change this into methanols. Right? So those bond polarities is very important, molecular polarity is very important. And to solve the problem is kind of tedious, so you just, yeah.
Wait, so it was polar because, why was it polar? Because it had different electronegativities?
Yeah, you see like this section about molecular polarity. Okay? So molecular polarity depends on 2 things. Okay? Depend on bond polarity, and then depend on the geometry. For the last one, depend on the geometry. For the last one, I draw that a small molecule. So there's only one center. Only one center. If the one center decides, you can use what we learned, the geometry, tetrahedra or the octahedras. So then from the bond polarity and the geometry decide this center is polar, non-polar. And then there's only one center. If this center is polar, then it is polar. When you have a lot of molecular, you have more center. Right? And you might have 3 center, 4 center, 5 center. So as the center increases, your problem becomes more and more tedious. So in this chapter, we're going to talk about, we are going to have one polar center. Right? And then we will think about all other centers is non-polar. Okay? Then we will gradually have those transitions. If you have one center with the polar, your molecule is polar. If you have 2 centers, then one center is polar, the other center is non-polar, you still have a polar molecule. If you have 3 centers, one center is polar, 2 other centers non-polar, you still have a polar molecule. Now you have 4 centers. You have one center is polar, the other 3 centers non-polar, you still have a polar molecule. Now you increase more. I think you have like 5 centers. Then you have like 1 center in the powder, the other 3 or 4 centers non-powder. Then your molecule become really on the boundary line, kind of not that powder. So then finally you will see you have more centers, so you only have 1 center in the powder. If you have more than 4 that are non-powder, then your molecule becomes non-powder, even though you have 1 powder center. So you have these 2 kinds of target water. So you can think about the starting from something simple. There is no center at all. No center at all, that means 1 single bond. Only 1 pair of atoms. If you have 1 pair of atoms, you don't have a single any center. Then your problem becomes simple. That means if your bond is polar, then your whole molecule is polar.
And you know your bond is polar because of those numbers?
You can use this to tell. If you don't have this, if all things all them are the same, sometimes they might still polar depending on the depending on the loose structure. Depending on sort of the long pairs. Right? So most of the molecules you can use those numbers. Right? Then sometimes you have to use long pairs. For example, ozone. You know loose structure of ozone, right? And you get this. And if you look out, you'll see ozone in the polar molecule. Okay? Which means it must have some polar bond in it. Okay? So then where does the polar bond come from? All the electronegativity for O are the same. So you do the subtraction, so O is 3.5, so you get 0. Okay? But those lone pairs are a little different. So there's only 1 lone pair on the middle, and then on the average there's a little more than 2 lone pairs on the side. Right. So now let's think about that, what I talked about. Okay? So when we talk about the polarities, you can think about there's a zero center. For example, HCl. Okay? And then you can think about the next possibility is 1 center. Okay? Then you will see 2 center. Okay? And so on. So then, if you have more than 1 center, then the 2 center may be different. Maybe 1 is polar, 1 is non-polar. Okay? So then that will become very, very tedious. Okay? To make the problem, make our discussion simple, we will think about, if you have more than 1 center, you probably think about 1 being polar, 1 non-polar. Okay? If you have both of them polar, that's difficult. You have to see what are the geometry, how they come out, and so on. Okay? So now, as a beginning class, so we will make our discussion relatively simple. Okay? So we first be able to identify whether you have bond polar or non-polar. We pretty much, for most of the bonds, you use the number. Okay? Got it? And if the number difference is more than 0.5 or more, is polar. Okay? So then to decide your molecular, which means you have more than 1 chemical bond, you can use those different ways. You can use vector addition, you can memorize, you can do something. So now I'm not going to talk about those, I will just show you one way. Okay? That one way is like this. So I'll tell you there are 4 different ways. Okay? All of them are written in the lecture notes. And some of them is from the book, some of them I just randomly come out with some of these crazy ideas. But now you can think about, so I like this slide. That means you just divide that 11 geometry into these 2 groupers. How many geometry we are going to start in this chapter? 11 molecular geometry. So that 5 is so-called the polar geometry, and they looks kind of not so good because they're not symmetrical. You can see, for example, this one is a square line. You have one on the top, there's nothing at the bottom. Okay? And there's a line here, the one at the bottom, nothing on the top. So this is kind of unsymmetrical. Okay? Now this few geometries is kind of symmetrical. Okay? So if you don't have on top, you don't have nothing at the bottom. Right? So those kind of symmetrical geometry, we call them a non-polar geometry. So now what you do, once you memorize this 2 group of geometry, a non-polar geometry, polar geometry, then just identify in those geometry do you have a polar bond. For this so-called polar geometry, any polar bond, no matter one polar bond, two polar bond, if you have two polar bonds, you have to think about are they the same or different? So then for this polar geometry, no matter what they are, if you have a polar bond, your molecule becomes polar. That's the name, polar geometry. Now for this sixth geometry, it's kind of called non-polar. That means if you draw the blue structure, you decide molecular geometry in one of those six, then if you don't have any polar bond, for all those geometry, if you don't have any polar bond, non-polar. Now for that geometry, any polar bond make it polar. For this geometry, you have a polar bond, not enough. You have to see what kind of polar bond. Now for this sixth geometry, if you have a polar bond, if all the polar bonds are the same, then you will cancel out. If all the bonds are polar and all if all the bonds are polar in this sixth geometry, and all of them are the same, then they will cancel out. Right? So if you have like all of them are polar bond, or some of them are polar bond, then obviously that means you have different polar bond. Right? The polar and the non-polar is different. Okay? So you have a different polar bond in this geometry, that's the only possibility to make them polar. Okay? So this, I think that's probably the easy way to solve the problem. Now I think about when we start in Chapter-1, we have those questions, so probably some of you like to answer questions, so I got that idea. But that is the same as in the last slide. Okay? So if you like that, answer those questions, you can use those. All right. I think we will finish this one and then we'll do the lab. So I will say that I first emphasize there are two groupers of geometry. Polar geometry and non-polar geometry. What are the five polar geometry? 5 and 6. Okay? 5 and 6. Now these 5 and 6 are different than the 5 diagonal geometry and 6 those geometries, so they are different. Okay? 5 polar geometry, one is this. And this is called what? Band. Okay? And the other one is dash and wedge and that. That we call that trigonal pyramid. Okay? And what else? Consider things, all the truck and that. And this is called what? T-shaped. Okay, so what else do we have? Any idea what the shape of this?
What? No, seesaw?
Seesaw. Okay, one more. You want to remember the other one? So this is called polar geometry, which means any polar bond in this geometry can modify the polar. Not symmetrical looks like.
Square with the.
Yep, so then one is a square, so you will have something like that. And what you have is one corner here, and one corner here, so then you have this middle, then one in square, how I can draw that? So I probably will draw that corner, and here, and like this, right? Right. So I probably should use dash here, and wedge here, and wedge here. Okay, what do we call this? Square pyramid. So these are 5 polar geometries, and then that's That 6 non-polar geometries, one is what? Linear, and one is trigonal planar, and then one is what? So this is a tetrahedra, and then one will be, this is called the octahedra, right? And then one will be our this. This is called what? Trigonal bipyramidal. Right. One last one. So these are the 5 geometry for the electrons, and one will be that the spiral, right? So I will simply draw like that. Okay? The spiral planning. Alright. So if you have this molecule in these 6 geometries, unless you have different polar bonds, different polar bonds, that will become polar. If you have that 5 geometries, any polar bond making molecule become polar. Okay? So you already know this molecule, right? So this NH3 like this. So let's see what is our MD for this. Very good. Trigonal pyramid. You know which one of these groupers? This trigonal pyramid is the sort of the polar geometry, polar geo, or the non-polar geo. So I grouped them a little different now, right? So sort of polar geo and non-polar geo. So this trigonal pyramid is the polar geo and non-polar geo. Polar geo, okay? So it becomes this. Okay? Now if you have this kind of geometry, your molecule will be polar if you have any polar bond. Okay? So this is our geometry. For this geometry, any polar bond in it, no matter they are all are the same or all are different, one is polar, the other one non-polar. Okay? So what bond we have in this geometry? We have A and H. Okay? Now the bond between A and H. What you do, you're going to use the electronegativity. What is the electronegativity for A is 3.0. The electronegativity for H is 2.1. Right? So delta EA becomes 0.9, which is larger than 0.4. So anything larger than 0.4 is polar. So therefore we have polar bond. Right? So step by step. You first see the geometry. Because the geometry, the polar geometry, then just examine any of the polar bond. If any one of the polar bond is polar, your molecule becomes polar. Okay? So our conclusion for this ammonium molecule is polar. It's so important, right? Because that means you have this electron on this end that can do a lot of chemistry. Yeah, they like this 3H. Sometimes this H can be replaced by a carbon. And by carbon like H or something like that. And then you will have all those, you can use this as a nucleophile, which means you have this electron negative, and that kind of taking some of those atoms that has the positive atom in it, and the positive atom usually means those carbon that are attaching to like oxygen or chlorine or fluorine, and then the reaction, you can have some of those kind of reaction. Right, so we will do the lab like we will write that's the one lab. Then next Tuesday, so I will give you the molecular model. You can do that molecular model lab. So today's lab, you just we have like a measure like those zero pressures, just like 40 temperatures.
You guys don't
Wait in the car after class day.
While the camera's rolling, I want to see I want to see everything.
But like, it was one of those where
It's going to be a great one that go watch
I have a plan.
so he said,
Would you guys?
and then said, over it.
have the lab, you guys are going to registry. Would you mind if I do the lab for next week?
I saw that.
Today? Like, I can at least, well, the one we didn't do last week, remember? I told you in the beginning of class, so it was one we skipped. Oh. Huh? Yeah, he said Tuesday, so I was gonna say, I can do that in class while you guys are doing the lab this week, that way we're doing the lab this week. I can get that done, while you guys do that. Then I guess.
It doesn't really benefit me to say